I am researcher Nofel Amadi and my colleague Naima from Al Janoub Stadium Group, and my supervisor Dr. Abdel Shakur and engineer Zawar. Our research is investigating the performance of novel LiMn2O4-MXene nanocomposite cathodes for lithium-ion batteries. This is our outline of our research. We will start with the introduction and research problem and so on till the acknowledgement. The components of coin cell. The top is the top case, followed by the anode, and then a separator because we can't put the anode, which is a negative ion, next to a cathode, which is a positive ion. So we use a separator, then we put an electrolyte to change it from negative to positive. And at last, the bottom case. Lithium-ion batteries. As we mentioned before in the research title, that our research is about lithium-ion batteries. We will start to talk about the components of these batteries. It consists of three essential components. First thing is the anode. It's the negative electrode that releases electrons to the external circuit and oxidizes during the electrochemical reaction. The second thing is the cathode. Is the positive electrode that acquires electrons from the external circuit. And at last, the electrolyte is the medium that provides the ion transport between the cathode and anode of the cell. We use these batteries in many applications, such as transportations, industries, and computers. Challenges of the battery. Challenges that the battery are facing are specific power, performance, cost, safety, lifespan, and stability. Our research objective is understanding the structure and working principle of lithium-ion battery. Our second objective is understand the importance and need to develop new anode materials for lithium-ion batteries. Our last objective is to study the electrochemical performance of the developed anode materials based on chemistry LiMn2O4-MXene nanocomposites. Novelty. Synthesis and characterization of advanced LiMn2O4-MXene nanocomposite as novel anode materials for lithium-ion batteries. Materials. The materials that have been used in our research are lithium fluoride, deionized water, max phase, hydrochloric acid, lithium hydroxide, oxalic acid, ethanol, potassium, and distillery. The equipment that have been used in our research are weighing balance, Dr. blade, centrifuge device, thermogravimetric analysis, microwave furnace, X-ray diffraction machine, battery testing machine, and scanning electron microscope and hydraulic press. Now I will leave you with my colleague Naima to start with the methodology.
Here is our research plan with 4 stages. Stage 1 is material synthesis. Stage 2 is structural and thermal characterization. Stage 3 is electrode and cells fabrication. And last stage is electrochemical battery characterization. This is our first stage, which is synthesis MXene from max phase. So we started with weighting 1.6 gram of lithium fluoride. Then we added 5 milli of deionized water and 15 milli of HCl. Then we left it stirring in the magnetic stirrer at 100 RPM at 35 Celsius. After that, we slowly added 1 gram of max into the mixture, then we closed the lid. We increased the stirring speed at 300 RPM at 35 Celsius for 24 hours. After that, we added the etching mixture to 150 milli centrifugation tube. Then we centrifuged the mixture at 3,500 RPM for 10 minutes, and we continued washing until the pH becomes more than 6. Stage 2 is synthesis of MXene nanocomposite by chemical co-precipitation technique. We dissolved 3.635 potassium permanganate to 50 ml of deionized water. Then we added 0.635 gram of MXene to the solution and stirred for 2 hours at room temperature. Then we poured oxalic acid into potassium permanganate solution dropwise. The solution was cooled and diluted with 500 ml of deionized water. The precipitate was treated and washed several times, and after filtration, we kept it drying in the microwave at 350 Celsius for 15 minutes, and then once again at 750 Celsius for another 15 minutes. The third stage is synthesis of MXene nanocomposite. 1 gram of synthesized MXene nanocomposite were dispersed in 50 ml of ethanol. We added 0.219 gram of lithium hydroxide in 50 ml of ethanol. The two solutions were put on the magnetic stirrer, and while they were magnetically stirred, the lithium hydroxide solution was added slowly to MXene suspension. The powder that we obtained after drying was preheated at 350 Celsius for 10 minutes in a microwave furnace. After that, the powder was heat treated once again at 750 Celsius for 15 minutes in the microwave furnace. The final stage is coin cell fabrication. After heating the materials, we prepared the slurry and then we coat it using Dr. blade. After that, by using the cutting machine, we prepared our electrode and packed it. And by using the glove box, we prepared our final cell, as you can see here. And finally, we started to test it. Now I will leave you with my colleague to start results and discussions.
We will start with physiochemical characterization for the materials. The first test is a scanning electron microscope. We use this device to show surface morphology of the sample. As you can see, figure A for MXene and figure B is for LiMn2O4-MXene. For MXene structure, the MXene as synthesized sample had a layered morphology resembling exfoliated graphite, where nanolayers were distinctly isolated from each other. In figure B, the developed LiMn2O nanoparticles preserve a homogeneous dispersion and MXene retains a well-laminar structure. The second test is X-ray diffraction to see the structure of the samples, and as you can see here, the four patterns. The first one is for max phase, the second pattern is for MXene, the third is for LiMn2O-MXene, the fourth is for LiMn2O. These sharp peaks show that the materials are crystalline and pure, which have a good property.
And now we will start with the electrochemical battery characterization. Cyclic voltammetry is an electrochemical technique that we use to show the electrochemical activity of the fabricated sample within the voltage range. So as you can see here, the y-axis is the current, and which is the flow of electrons, and the x-axis is the voltage. The voltage range is from 3.5 to 4.5. If we compare between these two figures, you can see the first LiMn2O in figure A, it has a thin, sharp peak, while figure B has fat LiMn2O-MXene. And we can see the rectangle, which means that it has more capacity for the battery. Here we have the galvanostatic charge discharge. As you can see in x-axis, we have specific capacity, which is how much energy it stores. So in the first graph, the LiMn2O has capacity approximately 100 milliampere hour per gram. And in the second graph, it has 110 milliampere hour per gram. That means when we add MXene, it has improved the properties of the capacity of the material, which is required for the battery. Here we have the rate capability results. If we compare between figure A and figure B, we can see that the capacity increased in figure B after adding the MXene to LiMn2O, and it has also improved the capacity for the LiMn2O. Conclusion. LiMn2O-MXene nanocomposites were synthesized and their physical and electrochemical characteristics were investigated during the proposed study. The CV data reveal that the LiMn2O-MXene electrodes' electrochemical reactivity conforms well to the discharge charge profiles. LiMn2O-MXene has a far higher capacity than the LiMn2O anode, suggesting that the pairing of MAX with LiMn2O nanoparticles is favorable for improved capacity.
The benefits to Qatar and recommendation. Our battery increases the productivity in Qatar. Also, it's a renewable source as it's low cost and rechargeable.